Start.
Share.
Share screen. Share this
Yeah,
one,
this one.
the messy one.
Pull out Maria's presentation on
No,
that.
no, because it's in the presenter's mode.
Okay.
So we need
Just play from start.
Play from start. Okay, perfect.
Hey everybody! All right, let's get started here. We're already a few minutes late, so if y'all could quiet down, that'd be super. I was mostly referring to the people who were talking about that. So we're going to start with Maria Rioja, who's going to tell us about the benefits of multi-frequency receivers for the ngEHT. Please take it away.
Okay. Yes. Good afternoon, everybody. Yes. So my name is Maria Rioja. My focus of research in the last decade, together with Richard Dodson, the next speaker, has been developing novel phase calibration methods to enhance the VLBI outcome with next generation instruments. So this talk is about the benefits of using multi-frequency receivers for ngEHT. So this is the outline of the talk. I will start stating some of the challenges in sub-millimeter VLBI observations, then the basis of frequency phase transfer techniques proposed to overcome them, and then this performance at ngEHT frequencies using simulation studies, and finally some implications of these techniques on the array capabilities, and finish with a summary. So as I said, of course, the main challenge in sub-millimeter VLBI is the fast phase fluctuation imposed by the variations in the water vapor distribution in the troposphere, and this results in all poor sensitivity and reduced number of suitable telescope sites and prevent astrometry measurements. So a very convenient way around these limitations in the centimeter regime is using phase referencing, which relies in interleaving observations of a nearby source, calibrators to eliminate the tropospheric fluctuations and extend the coherence time. So higher frequencies require faster telescope switches, and that's why this strategy breaks at some point, because the telescopes, there is a limit of how fast they can move. Also calibrator availability. So this in turn marks the beginning of the decline of VLBI performance at higher frequencies. So an alternative strategy to extend these benefits to the higher frequencies consists of using transfrequency calibration, which relies on the non-dispersive nature of the tropospheric fluctuations. So at heart is similar to phase referencing with the roles of sources and frequencies interexchange. So it was first tried with the VLBA using fast frequency switching, and the upper frequency limit for that is 86 gigahertz. So it's already a factor of 2 with respect to the phase referencing, how high you can go. And it requires a direct detection at the low frequency. And here I just say integer frequency ratio is recommended. Of course, the optimum performance is obtained with simultaneous multi-frequency observations. This has been demonstrated with the KVM up to its highest frequency, 130 gigahertz, and there is certainly no limit that we can think of for it to work. So here, the FPT calibrated high frequency data set, so using the low frequency, calibrate the high frequency, then you have a much improved coherence, and then it can be analyzed within a self-calibration at the high frequency, with a solution interval orders of magnitude longer compared with single frequency observations. So this is the observational setup used in the simulations I'm going to present. Just saying, an alternative option to this second self-calibration at the high frequency is to include interleaving dual frequency observations of a second source. And this is the basis of source frequency phase referencing observations, and that will appear in Richard Dodson's next talk on astrometry with ngEHT. So this two-step calibration, additionally to the extended coherence time and boosting of sensitivity, it delivers astrometry between the frequency bands. at sub-millimeter frequencies. Okay, so encouraged by the success of the successful story of the KVM, we propose to extend these FPT techniques to the ngEHT frequencies. And then we have carried out simulation studies to characterize the compensation for a range of atmospheric phase fluctuations. So I will guide you quickly through the most relevant steps. So we use ARIS to generate synthetic data sets with the tropospheric fluctuations implemented as phase screens, assuming Kolmogorov turbulences with the CW parameters to characterize them. So with higher values of CW, they stand for stronger fluctuations. And so we are using the best weather conditions. They are that with V for very good. It corresponds to a CW of 0.5. And then from there, we are doubling. And so it's worsening weather. So for G stands for good, and T, which stands for tolerable or typical. So then we generate single frequency and simultaneous dual frequency data sets at all the frequency pairs of the ngEHT and under all weather conditions. And then we carry out the analysis with AIMS. Using for the analysis of the simultaneous dual frequency observation, we use FPT strategies, which comprise of a self-calibration at the low frequency with a range of solution intervals given by tau low, which are 8, 15, 30, and 60 seconds. These are used to calibrate the high frequency, they stabilize it, and then we run there a second run of self-calibration with a much longer values of the solution intervals given by tau high, and they are equal to 1, 3, 10, and 60 minutes. Okay. For the single frequencies, we do the standard self-calibration imaging in AIMS. And then finally, we use the fractional peaks flux recovery from the images to indicate the coherence losses from the calibration that we have used. So let me show you the results of this. First of all, this is the empirical values from EHT. You will recognize it. This is on the y-axis is the coherence, on the x-axis is the solution interval of the self-calibration analysis, which extends from 1 to 50 seconds. So a 20% coherence loss results from a 40 seconds solution interval. And to the right, these are the results from our simulations for single frequency observations at 230 gigahertz for a range of weather conditions. B is the solid line, the solid blue line, G is the orange, and T is in green. And overplotted are the empirical results. The intermittent line is the empirical result from EHT, which match pretty well the result from the V, the very good weather. Okay, so this is very important because it confirms the realistic weather models that we are using in ARIS, where V corresponds to matches the EHT sites weather. And the other, good and tolerable weather, they are represent sites with worse weather or lower quality sites. Okay, so these are I'm going to show you just a touch of the results of the FPT analysis with dual frequency observations. These are at 340 and 230 gigahertz. So what you see here, they are again, like before, observations at 340 gigahertz in the very good weather. So from EHT-like sites. And that is the coherence, and this is the solution interval for the self-calibration at 340 gigahertz, now spanning from 1 to 60 minutes. And each color stands for the self-calibration used at the low frequency, at 230 gigahertz. Okay, so it's in seconds, and it's as indicated in the smaller box. And when you see here a 20% loss, with a very good weather, the coherence is very high and is maintained for much more than 1 hour with very small losses. And the same exercise under good weather conditions. And still, you see this, but the performance deteriorates. And this is due to mainly to the non-integer frequency ratio here. So this is caused by loss of phase ambiguity and causes coherence loss. For under tolerable weather conditions, the performance is very bad. So the coherence is not maintained. So this is the same exercise we are doing now for another pair, which is 340 to 85 gigahertz. So in this case, the simulations is here on the left is shown for the EHT-like sites, and these are the good weather conditions to the right-hand side. So in both cases, the coherence at 340 gigahertz is maintained very high for much longer than 1 hour, and with longer tau lows at 85 gigahertz that we had in the previous slide at 230 gigahertz. Also, even under tolerable weather conditions, a very high coherence is maintained for much longer than 1 hour for this frequency pair.
So the key issue that now is an integer.
Yeah. These are integer ratio, yes. Yes. So this is the slide before the summary, and I just want to highlight some of the key implications of the FPT methods on the ngEHT fundamental array capabilities. Okay. So first of all, FPT techniques, they result in a big boost of the sensitivity at 340 gigahertz because they extend the coherence time. And for example, extending it from 10 seconds to 60 minutes, it means that the number of sources that they are within reach, it explodes, is much higher. And also the FPT sensitivity, so using 340 and 85 gigahertz, is equivalent to observations at a single frequency at 340 gigahertz with an array which would be 400-fold increase in bandwidth or 4-fold increase in antenna diameter. Okay? So these are the implications of this extended the coherence time. Also, very important is that these FPT techniques relax the requirements for suitable sites and weather conditions. So it means that you can have many more NG sites which are suitable for sub-millimeter observations, and also means that you can observe more epochs across the year. So this is a very interesting plot that comes in the Dodson function in the 3rd edition, and it shows the relation that there are between the path stability and the site altitude. And so based on that, our simulation, what we have overwriting there is the indicative altitude of the weathers that we are dealing with the ARIS. So the very good weather, you remember, is Almaty. The good weather, it will be about 2,000 meters, what we are talking, and tolerable weather is really under 1,000 meters. And finally, the summary. These are other advantages. So finally, I just want to conclusion to say that the FPT methods, they are of strategic importance for ngEHT. They are the transformational adaptive phase correction capacity that reverses the main limitations of sub-millimeter VLBI. And this results in a robust performance of ngEHT, enabling high quality images for many sources and ultra-precise astrometry. Just to end, I had said in the beginning that you need to have detections at the low frequency. In the next talk, Richard will present solutions for the case of Sagittarius A, where you might not have due to the scattering detections at the lower frequency. Okay, that's all. Thank you.
We're gonna have time for like 1 or 2 questions, and maybe Richard, you can come up while that's going on. We can set up. Yvonne.
This is fantastic. I'm so happy to see this. So I want to mention, what would the principle prevent to go to even higher frequencies? So imagine that you go to factor 2 of 230, and you will have the electronics. Would it still be feasible, or there will be any
the performance in the simulations? It is pretty remarkable. I mean, I'm talking there of integration for 1 hour, and the coherence has dropped very little, maybe 5%. So as you go to higher frequencies, you would expect that you would have.
Yeah, but in principle, yeah.
By principle, yes, you have a room. Yes, I mean, it's our experience with the KDM is incredible. It's to see to believe it. We didn't see any sign of reaching any upper limit. You would have from empirically demonstration 130 gigahertz is pristine. Dom?
All right, maybe one more question, Remo.
Yeah, this is fabulous, of course, and superior. But has there ever been a comparison between water vapor radiometer directly corrections and tri-band receiver?
Yeah. So I'm not an expert in water vapor radiometer. I have talked to people about this, the ability. So my understanding is that in ALMA, the water vapor radiometers, they work very, very well because the site is quite special. There is a very low precipitable water vapor. Even in ALMA, when there is clouds, the performance of the water vapor really is much worse. And in other sites also, I mean, historically, the use of water vapor in sites other than ALMA, it has been tried. It's a very interesting field, but it's not a robust performance. For example, when there is cloud coverage, it deteriorates. So I think this is very robust in this respect. This is a robust performance, no matter how is the weather, you could adjust the solution interval and the low frequency.
We can just change the display.
I was just wondering whether there actually has been a measurement one-on-one to see.
Well, not that I'm aware of. In the KDM, there is no.
Okay.
All right. I think we're just about to have this one up, so let's thank Maria again. And next up, we have Richard Dodson, who I think is going to tell us about the benefits to astrometry of observations of SgrA star for multi-frequency.
Just make it mirror mode of the presentation, otherwise I'll have to be telling you.
Sorry?
Could you just make it mirror mode for the display?
Sure.
So I've lost my presenter notes, which means I might get confused. But we'll just have to.
Okay.
Just a mirror mode. Yeah. Fine. I've tried to make this super short. I've left a lot of stuff out that I'm going to say. I've even shortened the title. The title is impossibly long. I'm talking on behalf of the three of us who are on the current authors on the white paper to do with this. Myself, Maria, and Asaki-san, who wrote the simulator. Maria's covered all the stuff in black, so the coherence comes through beautifully. She touched on source frequency phase referencing as the method we use to get astrometry, and I'm just going to jump straight to this case in point, which is Sagittarius A star. Then I will say how conventional astrometry may be possible. Conventional astrometry at 86 gigahertz, that is amazing to me, but we think it can be done. Astrometry is between the frequencies, I think is a no-brainer. I'm absolutely confident it's going to work at 300 gigahertz. It's only tripling the KVN demonstration, and that worked perfectly. So with the increased coherence and the astrometry, you can do astrometrical surveys, and there's some interesting things to say there. So SgrA, so this was the question I think that Shep asked us. Will this work for SgrA star? And the fundamental thing in frequency phase referencing is it has to be easier to do at the low frequencies. If your source doesn't exist at the low frequencies or is scattered, so it's not detectable on the long baselines, that breaks it. So we went away and we had to think. We've decided that yes, we can make it work. So I'll just go on. I was going to say a little bit more about the ARIS. It was designed for phase referencing, so it's really suitable for phase referencing. Every simulator has its strengths. It's got really complete and complicated atmospheres, and that's why we think it's the right tool to use here. It's a bit old, but there you go. So turning to Sagittarius A star, we can put models into ARIS. So we put the scattering model taken from Sarah's paper from 3 years ago, I suppose now. And I calculated 170 by 80 microarc seconds for that scattering size. I hope that's right. It wasn't there written in black and white. I had to calculate it. So we put this model in, we generated the data, low frequency and high frequency, And this is the low frequency model, what the model looks like on a rad plot. One can either divide by that model, or you can just limit the UV range, and we took the latter. So I cut it at what is about equivalent to 3,000 kilometers, or 200 microarc seconds. And then you can make that work by, as long as every station has some 3,000 kilometer station against which it can be calibrated. So I call this a hub and spoke model based on the aeroplane models, the airline model. You'd imagine a cluster in South America around Elma, a cluster in North America around maybe LMT, maybe a little bit further north, European around Noema, and a South African cluster would be really good as well. So this is kind of a model of what I'm talking about. Each of those facets where I've drawn a ring around is calibrated separately, and then you calibrate those facets together. So you end up with just fewer, so you calibrate them where they touch. So this is a map of the stations used. So I have the 3 hubs. Simulators are great. Let there be a millimeter telescope on Kilimanjaro, another one in wherever, great. So much easier. And the results are fine. One of the things, I don't have a clock running. So I actually have no idea how long I've been talking.
You're about 4.5 minutes in. I'll give you a 10-minute warning. Stand up at 12 minutes.
Those are the results. This is a noise-free simulation. So this is the noise from the technique. So this is the noise we've generated through calibration methods. And those are about plus or minus 10 degrees. So that's pretty good. As we are able to calibrate all the data. The yellow is the 85 gigahertz UV tracks. And perhaps it's impossible to see like this, but the 85 gigahertz tracks are actually longer, more complete than the green, which represents the 340 gigahertz data after calibration. So it doesn't complete, there's some bits of data that drop out, but not too much. I should have calculated the fraction, I didn't, but your tracks are a little shorter because you've got to have overlap between the various facets. But you still end up with a pretty good UV coverage. And this is for Sagittarius A star, of course, which is why the southern African hub was important. The conclusion is Sag A star can be done. Bit of playing around, but it will work. So turning to what you can do with that, turning to, first of all, what we call lambda astrometry, a name I think we stole from Beaumont-Son, which represents astrometry between frequencies, not your conventional astrometry between sources. So we have, including Beaumont-Son, demonstrated lambda astrometry up to 130 gigahertz using the KVM. So that was the 129 was calibrated for both the 43. We tried the 43 and the 22. So we had an integer ratio in both of those cases, ratio of 3 and 6, it says here. And then we calibrate the dispersive residuals, so the simultaneous frequency observations, but no temporal interpolation from those. But then the dispersive residuals are solved for with slow switching between the secondary source, the second source in source frequency phase referencing. Those sources can be visited not so often because it's only the ionosphere, it's only small terms, they're changing slowly. We use minutes for the source switching, and you can go a long way. 11 degrees, we demonstrated. So that is definitely going to be possible for a 3-frequency ngEHT. Note that 2 frequencies this will not work because you've not got a good integer ratio, or it becomes really hard, too hard. So I would say this was possible. Lambda astrometry is possible for 3-frequency ngEHT. We've also demonstrated another method we called multi-frequency. The great thing about that is you didn't need a second source, but you had to solve for the ionospheric terms. You had to solve for and subtract the ionospheric terms beforehand. For that, we used here for a reason. We used low frequency terms which you don't have on ngEHT. So 86 gigahertz is too high to measure the curvature in the delay. So that's not going to work. It's a nice trick, but it's not going to work. And a I'll say it. And ngEHT has developed this triple frequency FPT squared method, which will work. It's entirely based on phasors. So that will be applicable, but it really doesn't deliver astrometry. It delivers a messy thing. I hope you'll forgive me for saying that, but it's not bona fide astrometry, so I wouldn't recommend it, but it might be useful. So turning to, there's a lambda astrometry, done that, conventional astrometry, and this is where we get a little bit crazy. We think this could be possible, and we think you can get amazing results. This is a plot from a review that we wrote recently, where we looked at astrometry, and where you described a method that we developed called multi-view. And in multi-view, you've solved for and removed these phase screens for both the troposphere and the ionosphere. You do it at the same time, because it's the same frequency. And so you're only left with the residuals to that phase screen that you fitted. Oh, I should say that an 86 gigahertz astrometry has been done. And Maria was one of the people who did it, and she didn't even mention it in her talk. But it has been done. It's been done once. No one else has bothered to do it because it was too hard and it really didn't work that well. The limitation is the switching. To switch so fast, you're only going to break the antenna if you do it for long. So it's a single demonstration. Losses were very high. It did get astrometry, but it hasn't been followed up. So the solution really is to go for simultaneous observations, no switching. So that means in the SgrA VLBI concept, the array will have multiple tide array beams. Or you could have a big single dish with multiple beams formed from the path. And that would also be useful for millimeter VLBI, only you would need field of view so small you couldn't have multiple beams from a single dish. You'd need a tide array approach or split antennas. Then reaching back to where I was talking, the multi-view is very precise because you solve for the phase screens. And this is an ionospheric phase screen. It's the piece of data that I had on the laptop. You can see how planar it is. So once you've subtracted off that planar fit, the residuals are really small. Ionospheric residuals set this slope, about a millitech left of noise, and tropospheric residuals, which we measured with the SMA. So they're really based on measurements, not just wishes. That comes down to a fraction of a millimeter, and I can't remember how much of a fraction of a millimeter, but it gives you about a 1 microarc second noise floor. Well, in fact, less than 1 microarc second. We add a microarc second for the calibrator stability. So, and this obviously only goes to 100 gigahertz, but you can extend it. And this line just extends to whatever frequency you want to go to. So we talked about this in the review. There's a big dish with multiple beams, and there's a tide array with an array with multiple tide array beams. We can take those values and calculate what sort of accuracy we expect. And for lambda astrometry between 85 and 340, the errors are dominated by the ionospheric residuals. Isn't that amazing? 85 gigahertz, and the ionosphere is the largest residual, but because you scale it up by these large factors. But we end up with 3 microarc second errors for a 6,000 kilometer baseline, because you get a phase, error term comes in degrees or whatever, and then you calculate the astrometric error. The multi-view astrometry requires that you've got simultaneous observations of multiple sources, but you're going to end up with a 1 microarc second error. And then this is almost the final point. The coherence means that you should have many, many targets. And I've taken these SFED values. One of them at least comes from you, and the rest I've sort of tried to extract from papers and what have you. So they could be wrong, but then combine that with the ALMA calibrator list, and we find 1,076 sources in the calibrator 6 with 3 frequency measurements, 3 suitable frequency measurements. And of those at 230, you'd get 200 odd detections. At 85 gigahertz, you get 970 detections, 5 sigma level detections. And at 300 gigahertz, only 80 odd. But with the frequency phase transfer, so 20%, 90%, and 8%. But if you were using the low frequency to calibrate, you'd actually have 200 detections at 340, or at 900 detections at 340. So this is why you'd now be able to do surveys. You'd have many, many sources to look at. And 2 types of astronomical survey that I can literally think of off the top of my head. One would be to look for the offset of the black hole blob, the peak of the black hole blob, to the peak of the 86 gigahertz blob. You don't have to resolve these into any kind of features. One being representing the foot of the jet, and the other one representing the actual inertial point of the black hole. So finally, we've measured, rather than guessed at, the separation between the black hole and the jet, or the shock where the emission is coming from. And the other one is the secular parallax that Andre talked about this morning. So I'll skip over that. The conclusions are there, you can read.
Richard. All right, Michael, I saw your hand first.
Yeah, so the slides you quoted for SgrA star, I think it is off, that calculation that's clerical or if it's different in the simulation. But, yeah, I think the source size is like 240 by 170. 240 maybe by 170.
Colin.
Can we get
Colin's?
Okay, that would mess things up. That was what I took out of the paper, so I would go for it.
I see.
We'll check on that, because that obviously changes things. But then you just reduce the more difficult.
Yeah, you know, it's really interesting. You could do this stuff in spoke model,
Yeah.
but the spokes could do phase transfer to 86, and for the hub connection, the long mix lines, you could actually do phase transfer from 230 to 86.
Presentation with more difficult.
High frequencies.
You've got to be careful with those 2 pi ends that we've now. Yes.
Play.
This opens up a long list of possibilities. We need to talk about that. Not quite.
We don't have
find
much,
out
but
Yeah, and it's just one.
All right, so let's get one more. Go, Paul, and then we'll move on.
Just give a good press of the button.
So we have one more question for you, Richard. Go, Paul.
So the multi-view concept that you had, in your cartoon, you had like multiple beams. Each of those are operating at different frequencies, or do you need that many beams?
Yeah, because you've got to have, and if you want to do conventional astrometry at 86 gigahertz, you can't switch, which means you have to be observing all the sources, 4 sources, perhaps, simultaneously. So you're going to have to, I'm going to ask my hub to be made of 4 dishes, and then you can do your normal stuff, and then sometimes I'm allowed to do stronger sources, where I point directly at those 4 beams, those 4 dishes point at 4 different sources. That's what I've asked for.
All right, let's thank Richard again. And next up, we have Colin Lonsdale, who's going to tell us about software correlation performance.
Okay, I'm reporting on the work that's been done at Haystack Observatory. Most of the work has been done by Antonio Vasquez. I'm just presenting it. So the problem here is understanding how to do efficient correlation for radio interferometer arrays. And the general problem is that you have a number of stations with the corresponding number of baselines. And as we know, the data rates can get very, very high, particularly in things like the ngEHT. So those data have to be brought together, precise time alignment. And the conventional way of doing this these days is an FX architecture. You Fourier transform it, and then you cross multiply and accumulate. That's very computationally intensive. And then you store the results and you control the whole thing using metadata. Then you have your correlator. Wish it was that simple. The challenges, of course, are very large data volumes and a lot of computational speed required. In the past, it has only been possible to do that using custom custom designed hardware. But more recently, correlator clusters have become dramatically more capable. So the preferred way of doing this now, even for the very large correlators, is to use a cluster and run parallelized software on it. So that's the software correlator. So the question is, how do we design clusters and the software that run on them to optimize the cost and performance ratio of our correlators? So this also applies to a variety of instances. So local hardware and cloud infrastructure, the thing is very application dependent. So one interferometer can be very, very different from another. EHT applications may well use a dedicated local cluster, which is what we're doing right now, a private cloud environment, which is essentially the same thing, or the commercial cloud. So there's a standard correlator performance metric that is typically used when figuring out the performance of a correlator, and that is the station data correlator ingestion rate in gigabits per second or some other rate unit. And that is how fast you can shove data into the correlator from each station individually and maintain the flow all the way through to the end product continuously. That's what the higher that number is, the better off you are. The total correlation time for a data set is given by your observing time, how long you've been generating this data, multiplied by the station digital data acquisition rate, which obviously we're headed towards 256 gigabits per second in millimeter VLBI, divided by this number R. So for example, if you've got an ngEHT array recording at 256 gigabits per second, and your correlator is sized and configured such that you can achieve an R of 10 gigabits per second, right there, then you end up with a month of correlator time needed to do 1 day's observing. The general goal for correlators is to maximize R per unit cost, because nobody wants to wait a month for every day of observation. So why characterize performance? So these are the kinds of questions that actually come up in real life. So VGOS is the VLBI geodetic observing system that's becoming a very large array with a very heavy correlation load. And somebody might be testing out software, seeing how fast it runs. And they find that this benchmark happens, that it takes 5 minutes for 3 seconds of data. And then you might want to know, extrapolating from that, how long will it take in Amazon Web Services with 20 nodes and 5 stations for 300-second scans? That's not an easy thing to get the answer for, because there's all kinds of bottlenecks in the system. Another one may be if you've got some execution time, is it cheaper or more expensive if I use fewer but higher capacity nodes in a cloud environment? That's a choice you make, and it's not always obvious how to do that. And then this is another reality of real-world correlation. You might be faced with something like this. I need to run a batch of 170,000 test correlations in order to fully characterize all the pathologies in my array and do pre-production and set up the production run in an optimum way with all kinds of automation going on. Is it better to run those in parallel or sequentially? Those are hard questions to answer unless you have some way of modeling what your correlator is going to be able to do. And the answers can translate to very large cost impacts. So here's the basic diagram of what a correlator does. You have your data sources, be it disks or a direct link or whatever it is. The data flows, streams into the correlator, and it gets then copied and distributed to processing nodes. And then the processing nodes take their outputs, go to a collection node, and you end up with the output data at the end. This is the number of baselines, this is the size of your input data at each station, and this is a factor that takes account of compression and averaging and different word sizes and so on. So that's what a correlator does. This is a traffic model that has been constructed for a, quote, ideal correlator. And you see various things here, these triangles. These triangles represent traffic scaling factors caused by data distribution, splitting of data streams, copying of data streams, averaging of streams down in the complex multiply and accumulate step, and so on. And then the Qs here represent the intrinsic limitations in the rate that things can propagate through the system due to the characteristics of the hardware. And one of the things to recognize is that these are designed to be things that can be readily measured. Like this one, for example, is the limit for a complex multiply and accumulate operation on a single core of a computer. That's something that is a basic unit. So these rates are not directly comparable, but they do, if you scale these things correctly before you go into this model, then you end up with a proper estimate of how much computational or bandwidth headroom you have at each step. There's a lot of parameters in a model like this. It's not a simple problem. Many different things describe the characteristics of the observation, the characteristics of the hardware, the characteristics of the parallelization and data splitting choices that you've made. And I'm not going to go through all of these, just to recognize that you have to look at all those factors if you really want to understand where your bottlenecks are going to be. So why do modeling instead of the traditional approach, which is benchmarking? You have your cluster, you have your data, you run it through setting different parameters, and you get a hard number at the end, how fast it went through. So benchmarking produces accurate real-world performance quantification. It's a specific implementation and parallelization strategy, specific hardware configuration and software settings can be varied, but it's time-consuming and labor-intensive, and there's a limited amount of that vast parameter space that you can actually explore in a meaningful way. All of those parameters, there's lots of different combinations. Modeling, on the other hand, is less precise, but you can much more easily explore a wide parameter space. So you can perform the generic benchmarks of these basic correlator hardware components, like a core, as I just said, or a network switch. And then you can assume that the software is written to achieve performance that gets reasonably close to those benchmarks. And then once you've done that, with this model, you can quickly and cheaply estimate the throughput for a much wider range of parameter settings. And that gives you insight, and it's the insight that you're after into optimal strategies for splitting, hardware choices, and cost minimization. And this can guide areas of focus for software development as well. There's some equations that you can derive that tell you what the limits are that are caused by reading the data off whatever media you've got, streaming the data around within the correlator, the data distribution limit, you've got to replicate the data, and there's a limit on how fast you can do your Fourier transforms, a limit on how fast you can do your complex multiplies, and there's various things that go into this that describe how your model is, the thing that you're modeling is set up. So how do you visualize all that? So you've seen this diagram already. There we go. This is a little bit unreliable, sorry. So these lines here represent the intrinsic hardware limits of what can be achieved. So this is the intrinsic level at which you can get data through a Fourier transform, for example, or that you can get data through a switch somewhere. They depend on various different aspects of the hardware system. And you can think of a particular setup and a particular type of experiment, a particular number of stations, as a line that looks like that, when it goes to past one of the triangles, there's a scaling, the data can be exploded or decreased. And then there's a level of throughput that is related to everything about the system that sets a certain number of gigabits per second in that particular part of the system, maybe in one core. So what you do is you take that shape, which is unique to your simulation, and then you push this whole line up until you hit something. In this case, you hit the data distribution limit. So in this particular configuration, you're limited by taking the data and spreading it around to your different processing nodes. So let's have a look at some actual, and the other thing to remember is that this parameter, the one that I mentioned at the beginning, is defined by how high this line gets at the left-hand edge when you push this thing up as high as it can go. So here's a number of simulations that have been run. This one is a real small one, 4 stations, 1 node, and 4 cores per node. And you see that you're limited by the station-based processing, the Fourier transform. So what happens if we start increasing the size of our correlator? Well, if you go to 2 nodes and 8 cores per node, then various things get faster, but you're still limited by the station-based processing. If you increase it still further, you're still limited by that. If you go up, however, to 4 stations, but this time with 8 nodes and 8 cores per node, all of a sudden you're actually limited by your ability to stream the data. Okay, so let's keep going here. Now, if you keep on going to make your correlator bigger, you're currently limited by data streaming. And now we go to 16 nodes. Well, you're still limited by the data streaming, so nothing's getting any faster. This thing is still stuck at the same level. But now, because you've got more hardware in the correlator, there's more headroom to speed things up if you could get the data to it faster. And that keeps on going, like that. So now, if we start increasing the number of stations, 4 stations is not very much. And we have interferometers with many more stations than that. So now you start eating up that headroom in the computation, and those curves start coming back up. And then at some point, you find that all of a sudden you've got 32 stations. That's a whole lot of baselines. Lo and behold, you're now limited by the baseline-based processing. Right there. And you can keep on going, and the same phenomenon happens. If you go to 64 stations, then all the others go down, but you don't go any faster. Okay, so now if we just increase the relevant resource to stop that being the bottleneck, then all of a sudden you've got so much data being churned out by this that you run into a limit in collecting the data. So this is an example that shows you, as you change your parameters, where your limits are and how much headroom you have. I mean, if you're going to be spending a lot of money on this, it's a waste because you're never going to be able to hit that limit. And so this is where you get the insight. And this is not something that you can do easily with benchmarking. It's take forever to do all the benchmarking to figure this out. So does it work? Basically, yes. There's a lot more model verification that needs to be done. But what's out there so far in the literature is, pretty promising. There's different kinds of limits that are shown on these graphs. This is numbers on the left is the number of stations, and on the right is the number of compute nodes. And you can see that the model is predicting limits. You can see that this the limit on data streaming the limit on data streaming is starting to show up in the shape of this curve, at least, even if it's underperforming. You have to assume that you're getting 100% of the raw capability of the hardware for those curves to actually land on top of each other. But basically, it's giving you the right insights, is the bottom line. But there's a lot more benchmarking that needs to be done to do the validation of the model like this. And also there's more parameters that one can introduce into the model. There's still major simplifications in the model. So the next steps, this is my last slide. As I just mentioned, further validation is needed, and we want to look not those with defects in the defects benchmarks. We want to use different correlation software implementations as well. We want to explore architecture trade-offs when using accelerators. This has just been CPUs in those simulations and modeling. Use the model for software architecture guidance and hardware choices. And in fact, an early version of this type of thinking was used to set the parameters for the haystack correlator for the ngEHT. And then finally, there is a paper describing this model in great detail that'll be submitted shortly. That's it.
Thanks, Colin. We have time for maybe 1 or 2 very quick questions. Maybe Nimesh, you can come up and start getting ready in the meantime. Go ahead.
Well, very interesting. I only agree that benchmarking is not an option, especially if you have many possible configurations. So one thing that's sort of common knowledge is that part of the correlator was linear number of tenants and very fixed cost. So that is the common knowledge is very common. The experience is that the turnover is about at stage. Can you reproduce that sort of knowledge easily with the model?
I think you do that using benchmarking. I mean, in general, there's station-based things that happen and there's baseline-based things that happen.
But your model should predict such a.
Yes, and that's what those couple of simulations that those couple of benchmarks that I showed. I wanted to point to a case where that is indeed showing up. So I have no reason to suspect that the model wouldn't pick up on that very nicely.
Yeah, I thought it was happening actually. Those slides. My questions were quite similar to Mark's, but in my case, I felt like your answer was what you inspired and what you asked about GPUs as well. I think if you look closely at the presentation, where he showed the implementations for various antenna numbers, various test conditions, it was up into the top.
Yes, it was
Up
flattening out.
into the top here initially, and then when it became input rate limited, the constraint was the baseline processing.
Yeah.
That's across the.
Our sense is that it's basically working and giving you about the right answers. But of course, the benchmark suffers from inefficiency in code. It suffers from overheads in the real world of various kinds, some of which are not included in the model. So you do expect the lines to be a bit below the nominal performance limits indicated by the model.
All right, and I think Nimesh's talk is still downloading. I saw a loading bar there, so maybe Remo, you want to answer your question?
Yeah, well, do you have any initial outcomes for cloud correlation?
Well, this is really totally agnostic, right? This is about running things through. You can figure out how to get the necessary value of R that you need for an application like the ngEHT or the SgrA or something else, and then say how much would it cost. Here's an optimum architecture that uses the minimum amount of resources to get the rate that you need. How much will it cost if you use the commercial cloud, if you buy a cluster, or if you do something else? And you can make the right choice.
Yes, but you haven't tried to just.
No, those are just concentrating on describing the model and explaining why it's useful.
All right, it's almost ready here. Is any other questions, Richard?
I'd like to know if you play with XF, all right. Can you change the model radically?
It would be a very straightforward change to accommodate XF correlation. All the runs have been done using FX. I mean, you just switch with things around there. It's really.
It might be a space question. It's not going to be, if you're not.
It's possible that it's going to be the best way to go forward in some circumstances. We certainly want to make sure.
All right, let's thank Colin again. We're unfortunately running quite a fair bit over, but we do have this half hour, what looks like in the schedule of wiggle room that we're just going to start eating into. So next is Nimesh Patel, who's going to tell us about some considerations for designing ngEHT antennas.
Thanks, Dom. So in the last couple of days, we have heard from a number of talks from Shep, from Michael and Janice about the plans for the ngEHT, split up in this various phases. The basic idea is to add up to 10 new antennas for the ngEHT array, which will be working together with the existing EHT array. And the science case is well described in the previous talks. So in this short talk, I want to cover these points. I want to just summarize a few lessons that we can learn from the deployment of SMA and the GLT antennas. And I want to briefly summarize the antenna specifications, which we are still working on. And finally, I want to briefly talk about our plan of refurbishing 3 of the BIMA antennas, which are currently at the overall site. for the 3 new ngEHT sites. So this is figure 7 from the Astro 2020 white paper on the ground-based EHT new arrays. And this Lindy Blackburn has done this calculation, which shows that you can have an antenna as small as 6 meters in diameter. And although not stated in the figure caption, the assumption is that this antenna will have aperture efficiency of 0.8. And it can be at a site which is not necessarily the Mauna Kea type or an extremely good site. It can be a site with some reasonably kind of 0.6 tau kind of atmospheric optical depth. And yet, such an antenna will be very useful for ngEHT as long as we have anchor station with a large collecting area, such as from LMT or from or from ALMA. So given that possibility, we started thinking of small antennas, even smaller, going down to something like, say, 4 meters. And the idea there was that we can containerize such an antenna and ship it to some of these extreme sites, which are hard to reach, and the transport of the antenna actually becomes a very expensive proposition, like what is happening now to GLT, for example. But then we are not sure yet of what this optimal diameter is. And that is one of the things we are working on at the moment. The advantage of sort of taking a shortcut now is that we already know that the GLT antenna, we can think of the GLT antenna as one of these new ngEHT antennas. We haven't done anything like, going from 2017 EHT to now, we have this antenna as a new station, and it has satisfied all the requirements for the performance we need for EHT observations. We have empirical proof of that. All 3 bands are working, and so why not just build 10 more of these? Yeah, that is a good solution, I think. You can certainly do that. And it's a question of cost. So regarding lessons, well, I think that will be a much longer talk. But SMA, these are some early pictures of how we built the SMA antennas, starting in 1994 from the Haystack site, where the first 3 antennas were built. We also did holography from there. We even did interferometry with 2 of those antennas. And there were major problems with this initial design of the antenna. There was complete lack of symmetry. This is one of the requirements I want to see in the new ngEHT antenna. There is complete lack of balance. And many of those problems are still around despite our implementation of some ad hoc counterweights. These are some more pictures showing those early days. And I want to emphasize, you should look at the year. I want to emphasize that it has taken something like 10 years. So going from the Haystack days to operation at the summit, Mauna Kea. That is Jim, by the way, our director, receiving one of the antennas shipped from Westford. Similar story has happened for GLT, where GLT was an antenna in at the VLA site, and our colleagues from ASIA and also from SMA, we started refurbishing and trying to figure out what are the components that need to be replaced in the drive system. Here is very young Satoki and Hiroaki, and we also did photogrammetry. Yeah. And we went through this process of identifying the parts which need to be replaced, and disassembly of the antenna, new servo components, new antenna computer unit, testing out the reassembly part at Norfolk. Already it is 2016, so it is already 4 years after we started working on this project. And then finally the antenna's parts arrive at Thule. And it is completely assembled and working on this date, 10th August 2017. And this is a very, very remarkable achievement. And thanks mostly to our colleagues from SgrA, many of whom are here. So after this, of course, ngEHT has been in operation continuously for EHT. So what about the specifications? What kind of antenna do we want? So I mentioned this diameter question, and my colleague Aaron Oppenheimer is working on this cost modeling calculation to arrive at this optimal diameter. Because if it turns out that we can get at a reasonable cost larger than 6 meters, something like say 9 or 10 meter diameter antenna, we can get a much improved sensitivity. And on the other hand, if we have to go with say 6 meter type antenna, we could possibly have more number of them, and that is one other strategy. By now you have probably skimmed through this. There is nothing really fundamentally new here, and that is what we want. We don't want anything new. We don't want to invent anything new. We want to use established numbers which have been used in the past for other telescopes. But let me point out a couple of things which we actually learned from the EHT observations which we have already carried out. So for example, we want an antenna that doesn't have any limit down to low elevation. It is very important to be able to go down as low as possible, even for a short time. And this is not possible for SMA antennas, for example, due to those mechanical design constraints. So SMA antenna lower limit is 15 degrees. The ngEHT antenna can go all the way down. And it is important to be able to observe the sun, not because we want to necessarily study the sun, but we don't want this sun avoidance constraints in observations. And that is a major limitation for SMA actually. These are, by the way, not the complete set of specifications. We have a draft right now of 3 or 4 pages document, which we are beginning to discuss with antenna vendors. And also not clear at the moment is what will be the limits in the operating conditions. That is again a very important driver. So it may turn out that some particular antennas for particular sites with extreme weather conditions will probably require different parameters. But in the end, we do want to have identical antennas, the new antennas, and a good model to follow, in my view, is the NRO VLBA, because they have actually gone through this process extremely rigorously in the past. And in fact, if you go through those memos, there is much to learn from them, particularly Peter Napier's memos on the antennas itself. And in fact, Peter was on the SMA advisory board. The modern operational stuff, not just the antennas, but even the operation part is something we should try to emulate. The last thing I want to talk about is the BEMA antennas. So here's a picture. I was at the site at Ouro to have a look at these antennas and assess their condition, and try to figure out what are the refurbishments we need to do to be able to use them for this phase 1 ngEHT. So here is Dick Plambeck and Mark. They are showing me around these antennas. You will notice that, so these are the 3 BEMA antennas. That is the historical 40-foot telescope in the background. And you'll notice that one of the antennas doesn't have this insulation cladding panels. So that is certainly one of the refurbishments we need to do. The surface itself is in very good condition, supposed to be about 40 microns RMS. So that will allow us to go up to 345 gigahertz. Of course, we will have to set the dish again following photogrammetry. And some drive component system in the drive system needs to be changed. So for example, they have this inductor scenes for the measurement of azimuth and elevation axis. Those need to be replaced by absolute optical encoders. And the stepper motors also may need to be replaced, which will allow us to actually have more modern control system and a better software interface. So that is the summary of my talk. The plan is that if this works out, we are actually thinking to deploy the 3 BEMA dishes to the Canary Island site, the Baja California site, and the Las Campanas site. I want to thank my friends Aaron Oppenheimer, Mark Freeman, Garrett, and Shep. So we meet every week once to chat about antennas. And these are some of the things we have discussed so far. Thank you.
Nimesh, we have time for a couple of questions. Start here.
Yes, Nimesh. Do these BEMA antennas have the capability to work simultaneously as per our frequencies? Like it has been said that this will be an important point.
Yeah, that's a very good point. So the receiver, we have dimensions of the receiver cabin. We have compared Gopal's new receivers dimensions and concluded that there is enough room. We want to have an ability to have a couple of people around able to work comfortably. And also it's a very simple, straight Cassegrain optics. There are no mirrors involved, there is nothing. So the ability to do simultaneous observations depends now entirely on the receiver design. But there is no constraint from the antenna.
I actually have 2 questions.
Yeah.
So you have mentioned that first you mentioned that you can do it with the smaller dishes so that you don't have to go to the cycle won't have to be that good. So you make a statement that you can use a smaller dish, but you don't know how small it can be. I mean, from the construction and management point of view, I'd like it to be as small as possible.
Yeah, so I think the answer there is a 6 meter is as small as possible.
That's the smallest.
Yeah, because one other constraint, apart from sensitivity kind of calculations, from our own experience, we know that if your dishes are too small, as single dish, commissioning and pointing and those kind of measurements also become difficult. So SMA 6 meter antennas, for example, we always do interferometric pointing. We don't do single dish pointing. And I think 6 meter, in my view, should be the absolute minimum in diameter.
Because that's a model, and you give it a safety factor of 50%, something like 3 meters.
Yeah, I mean, that is something we are figuring out. It could be a 10 meter diameter.
My second question regarding your specification, rough specification. Now, from the Greenland telescope's experience, we take advantage of ALMA development. So we just why do we develop new receiver, new capture? We just do something like ALMA has.
What is, yeah.
Band 3, band 6, band 7. I'm using their price tag, right? Then I give you a definition of your telescope, F8. Right? It's an F8 telescope. Then the next parameter you need to decide is the size. 8 meter, 9 meter. Right?
Yeah. Is that simultaneous? Is that simultaneous?
No.
That kind of, so
What's that?
you can use the system of things simultaneous.
It's not a triangle receiver.
Oh,
So that will be accurate, right? For this.
Yeah.
Well,
By the way, I just want to comment that receivers are out of the scope of my talk. I'm here